So let's continue working with concavity in the second derivative. And again, this would be a good exercise for you to try on your own before I do it. Here we're given the function x squared e to the x, and we're asked to find where it's concave up and concave down, and to state any inflection points as ordered pairs. Now would be a good time to pause to try this one out on your own. Alright, this again is continuous everywhere. Alright, so it's continuous for all reals. Let's calculate some derivatives. Alright, so g prime of x would be 2x e to the x plus x squared e to the x. And I'll do a little factoring here. That would be e to the x by x squared plus 2x. Then g prime of x, g double prime of x, the second derivative, would be then e to the x times x squared plus 2x plus e to the x times 2x plus 2. And again, if we do some factoring here, that would be e to the x times x squared plus 2x plus 2x plus 2. So it's x squared plus 4x plus 2. Alright, so there's our second derivative. And now it's never undefined. Let's find when it's equal to 0. So now let's solve. G double prime of x equals 0. Well, e to the x can't equal 0. X squared plus 4x plus 2, that equals 0. It doesn't factor, so it will apply the quadratic formula. X would be negative 4 plus or minus the square root of 16 minus 8 over 2. 16 minus 8 is 8, and that simplifies. So x is negative 4 plus or minus the square root of 8. Since 8 is 4 times 2, that's 2 root 2 over 2. And so then x is negative 2 plus or minus the square root of 2. So we have two critical numbers. 2 minus the square root, negative 2 minus the square root of 2, negative 2 plus the square root of 2. My number line, negative 2 minus the square root of 2, negative 2 plus the square root of 2. And now if you need, you can approximate these to get some understanding of where these numbers are. Negative 2 minus the square root of 2, that's negative approximately 3.4. Negative 2 plus the square root of 2, that's approximately negative 0.6. Alright, so now we'll test in each interval. Testing a number to the left, how about at negative 5? G double prime at negative 5. Using e to the x times x squared plus 4x plus 2, e to the x is positive. X squared plus 4x plus 2, well, I mean, we can throw in the negative 5 and test this out, or we can think of that being a quadratic, a parabola, opening up, and we know it has two roots. So it must go from positive to negative to positive. But if we throw in the numbers, let's just verify this. Negative 5 squared is 25. 4 times negative 5 is negative 20. So I've got 25 minus 20 plus 2, which is 7, positive. So that's a positive. And again, this is for G double prime. And then how about a number between negative 3.4 and negative 0.6? About negative 2. E to the power is positive. Now negative 2. Negative 2 squared is 4. 4 times negative 2 is negative 8. 4 plus negative 8 is negative 4 plus 2 is a negative. And then finally, how about we test 0? G double prime at 0 is obviously positive. Conclusions. G of x is concave up on negative infinity to negative 2 minus the square root of 2, union negative 2 plus the square root of 2, comma, infinity, is concave down on negative 2 minus the square root of 2, union negative 2 plus the square root of 2. Sorry, that was poorly written. That shouldn't be a union. There should just be a comma there. That's a single interval from negative 2 minus the square root of 2 to negative 2 plus the square root of 2. And we see the concavity change from positive to negative and then from negative to positive at each of those important values. And so we can find those ordered pairs. G of x has inflection points. And here I'll use some approximations. So we'd have negative 2 minus the square root of 2, and I'll take that value and substitute it into the function. So my function is x squared times e to the x. And let's substitute negative 2 minus the square root of 2. And that gives me approximately 0.3835. And at negative 2 plus the square root of 2, that gives me 0.1910. And so there are the inflection points for the curve. All right, so now let's take what we've learned so far about the first derivative and the second derivative and use some algebra. And let's sketch a function. And we're going to go into much more detail with this in the next topic, but we already have a bunch of ideas for this. Given this function, use algebra and calculus to analyze the function and sketch the function. Let's use everything we've learned so far in mathematics to sketch this curve. All right, what do we know from algebra? Well, it's a polynomial function, and so it's defined everywhere, right? The domain is all reals. Can we find any intercepts? A y-intercept, that's easy. The y-intercept, we let x equal 0. If we let x equal 0, f of 0 is 0, so we have a y-intercept at 0, 0. X-intercepts. We let y equal 0. Let f of x equal 0. And so that would mean we'd have x to the fourth minus 6x squared equals 0. So that's x squared by x squared minus 6 is 0. So x equals 0. Or x equals plus or minus square root 6. So we have 3 x-intercepts. We have negative root 6, 0. We can have 0, 0, which was the y-intercept. And then we have root 6, 0. So there's some information from algebra. Now let's use some calculus. Let's calculate the first derivative. F prime at x would be 4x cubed minus 12x. And we can find the critical numbers. This is defined everywhere, so let's set this equal to 0. 4x cubed minus 12x is 0. So that's 4x by x squared minus 3 is 0, which implies then that x is 0, or x is plus or minus the square root of 3. And we set up our number line, and we test into the first derivative. Negative root 3, 0, root 3, testing into the first derivative. Testing a number less than negative root 3. How about negative 2? So that would be a negative number times a positive number. That would be negative. Between negative root 3 and 0, testing at negative 1. That would be a negative times a negative, which is positive. Testing a number between 0 and root 3. How about 1? 4 times 1 is 4. 1 squared minus 3 is negative. That would be a negative. And then finally, testing a number greater than root 3. How about it 2? That would be 2, 8. 8 times 1 is positive. So what does this tell us? The function is increasing on negative root 3 to 0 and on root 3 to infinity. The function is decreasing on negative infinity to negative root 3 or 0 to root 3. What else do we know? We see the function was decreasing, then increasing, then decreasing, then increasing. It's switching, which means we have some relative extrema. Decreasing, then increasing. We know that f has at least a relative min at negative root 3, and then we'd have to evaluate the function at negative root 3. So negative root 3 to the 4th, that would be positive 3, 9. That would be 9 minus 6 times 3. 9 minus 18 is negative 9. It has a relative max at substituting 0 into the function. I'd have 0 minus 0. 0, 0. And again, a relative min at root 3, and it ends up being negative 9 as well. So there's all that analysis from the first derivative. And then we analyze with the second derivative. But we did this earlier, right? We did this in the previous video, but earlier in this topic I used the same exact function. Let me pull it back up real quick. So here's what we learned from that. We found that the function was concave up on negative infinity to negative 1 and 1 to infinity, concave down on negative 1 to 1, and inflection points at negative 1, negative 5, and 1, negative 5. So let's bring that information over. So I just copied that information over. See, now we can use all this information to draw a reasonable sketch of the curve. We know where it's increasing, decreasing. We know where it has its relative extrema. We know where it's concave up. We know where it's concave down. We know where it has inflection points. So to help with this, what I'm going to do is I'm going to take my number line and I'm going to break it up further using all of the important numbers that I found from the first derivative and the second derivative. So my important numbers from the first derivative were negative root 3, 0, and root 3. And then from the second derivative, we're at negative 1 and 1. So if I take that, let me take my number line. And again, what am I doing? I'm taking my number line and I'm breaking it up over all of those important numbers. We had negative root 3, negative 1, 0, 1, and root 3. And now what I have to do is think about the concavity and whether it's increasing or decreasing on each interval. Over negative infinity to negative root 3. Let's see, so let's go with the first derivative first. The first derivative was negative, and then it was positive all the way to 0. And then it was negative to root 3. And then it was positive again. The second derivative was positive on negative infinity to negative 1. Positive. And then it was negative to 1, and then it was positive again. And so this gives me a good guide for how to sketch the curve, because there's only 4 ways I can draw a curve. If it's increasing, it's either concave up or concave down. If it's decreasing, it's either concave up or concave down. So let's understand what's happening here. Over this first interval, between negative infinity to negative root 3, the curve is decreasing and concave up. Decreasing and concave up. How would I draw a curve that's decreasing and concave up? Okay, so decreasing and concave up, it might look something like that. That's a curve that's decreasing and concave up. Now it's increasing and concave up. Increasing and concave up. Then it's increasing and concave down. Increasing and concave down. Decreasing and concave down. Decreasing and concave up. Increasing and concave up. That's the basic shape of the curve over each of those important intervals. Now we just have to fill in the details. What are the relative extrema? What are the inflection points? Where are the zeros of the curve? All that sort of stuff. And so now we can bring that all together and actually draw the curve. Alright, so I brought in some axes real quick. And let's call it x and y. Right, there's my x-axis and there's my y-axis. And we had important numbers, important values at negative root 3 and at negative 1 and positive root 3. So here's the scale. There's negative 1. There's 1. There's 2. There's negative 2. For the y values, let's look at our y values. What was important for our y values? Negative 9 was an important y value. Negative 5 was an important y value. So let's bring those in. Alright, so let's say here's negative 5 and here's negative 10. Let's plot the important points that we have. We have x-intercepts at negative root 6, 0, and root 6. Let's plot those. Square root of 6 is a little bit more than 2, isn't it? So let's say that there's an x-intercept and there's an x-intercept. And of course at the origin we have an intercept. What else did we have? We had relative minimums at negative root 3, negative 9. The square root of 3 is about 1.7. So I've got about 1.7, negative 9. There's a relative minimum. And similarly over here, negative 1.7, negative 9. There's my relative minimums. Where were my inflection points? My inflection points were at negative 1, negative 5, and at 1, negative 5. There's all the important information. Now I just have to finish the curve. The curve was decreasing and concave up, then increasing and concave up. Decreasing and concave up. And this point is negative root 3, negative 9, then increasing and concave up. Then it switches to concave down. And then it switches back to concave up. Again, this point is root 3, negative 9. And now it's concave up. And so here's a sketch of the curve. Now that was a lot of work for this. Right? So this was the function x to the 4th minus 6x squared. And so that was a lot of work just to draw one curve. We're going to get a lot more practice with this in the upcoming topic. So, but this is a process that we'll use. We're going to use algebra. We're going to use calculus to get these important points and understand the shape of the curve so that way we can sketch it. Okay, so also related to the second derivative is a test called the second derivative test. And it's a test that can be used to possibly identify relative extrema when the first derivative test might be difficult to apply. And here's what it says. First, c must be a critical number where f prime of c is 0. All right, so it's a critical number, but it's a defined critical number. And the second derivative must be continuous near c. And then if the second derivative is negative, the second derivative is less than 0, then x equals c is a relative maximum. All right, so understand, right? The second derivative is negative. It's concave down. So I have a stationary point, right? This means we have a stationary point. A stationary point concave down. If you think about that, if you have a stationary point and concave down, it's got to look like that. Right? That's the stationary point, concave down, relative maximum. If, however, the second derivative is positive, now I have a stationary point and it's concave up. Concave up, stationary point, relative minimum. If, however, that second derivative is also 0, then the test is inconclusive, and you have to rely then on the first derivative test. So let's again look at the function x to the fourth minus 6x squared, and let's recall that f, the second derivative at x, was equal to 0. Let's see, that was just a moment ago, but I've forgotten already. The second derivative was 0. I'm sorry, the first derivative was 0 at 0 and positive or negative root 3. All right, and that's not the second derivative, that's the first derivative. The first derivative of x, of f of x, was 0 at 0 and plus or minus root 3. And the second derivative of x was then 12x squared minus 12. So notice that f double prime at 0 is negative 12, which is less than 0. What this tells me then, we had x equals 0 was a critical number of f, and the second derivative was negative. So that tells me we have a relative maximum when x equals 0. If I take the second derivative at negative root 3, the second derivative at negative root 3, that would be 12 times 3, that's 36 minus 12 is 24, which is positive. So now I have again, I have a critical number. Positive root 3 is a critical number, and now the second derivative is positive. So that tells me I have a relative minimum when x equals negative root 3. It turns out to be exactly the same when x is positive root 3. So I'll just write plus or minus root 3, and it works for both of those. And so here's another way that we can find relative extrema through the use of what's called the second derivative test. This is often very useful in applications, especially applications where we don't have, where the functions we work with are not all numerical. Sometimes we'll have functions that involve other parameters, and so this second derivative test is often very useful in those situations. Let's see one more example of the second derivative test. Here's a problem from Paul's notes. We're given this function. We're asked to determine the critical numbers of the function and then use both the second derivative test and the first derivative test to classify the critical numbers. So let's first find the critical numbers. We have the function x plus 1 cubed by x minus 1 to the fourth, and I will use product and chain rules. So f prime at x, say that would be 3 by x plus 1 square by 1 by x minus 1 to the fourth plus x plus 1 cubed by 4 by x minus 1 cubed by 1. So what can we factor out here? I can factor out an x plus 1 square and an x minus 1 cubed. And let's see, then that would be 3 by x minus 1 plus 4 by x plus 1. So that would be x plus 1 square by x minus 1 cubed by 3x plus 4x, that would be a 7x, minus 3 plus 4, 7x plus 1. So let's see, my critical numbers then. Critical numbers are at -1, -1/7, and 1. Those are my critical numbers. Now I have to find the second derivative if I'm going to use the second derivative test. Now this is not fun, but we learned how to find second derivatives. We learned how to find derivatives of derivatives, and all I will do is apply the chain rule several times. So in fact, if we apply the chain rule, if we have 3 factors, we basically leave 2 factors alone and find the derivative of the third factor each time. Alright, so the second derivative would be 2 times x plus 1 to the first. Leave the others alone. X minus 1 cubed, 7x plus 1. Plus, leave the first factor alone. X plus 1 square. Take the derivative of the second factor. 3 by x minus 1 square by 1. And then times the 7x plus 1. Plus, now leave the first 2 factors alone. X plus 1 square, x minus 1 cubed, 7. Alright, what can I factor out? I've got a common factor of x plus 1 to the first power. I have a common factor of x minus 1 square. And that's the only common factors. What's left? In the first term, I have 2 by x minus 1 by 7x plus 1. In the second term, I have 3 by x plus 1 by 7x plus 1. And in the last term, I have x plus 1, x minus 1 by 7. And so now I've got to simplify that mess. So this is x plus 1 by x minus 1 square by, I'm not going to do all the work for this. I'm going to find it and then just write it. Now I'll go ahead and write it. So let's see, that's 7x squared, 14x squared. And then I'd have a minus 7x and a plus x. That's a minus 6x minus 12x. Minus 1 times 2, minus 2. Alright, then I'd have a plus 7x squared times 3, 21x squared. And then a plus 7x and a plus x, that's a plus 8x times 3, that's a plus 24x. Plus 3. X plus 1 times x minus 1 is x squared minus 1 times 7. That's a plus 7x squared. And a minus 7. So that's x plus 1 squared. I'm sorry, x plus 1 by x minus 1 squared by 42x squared plus 12x minus 9 minus 6. Alright, so now that we have that, applying the first, okay, we have the critical numbers, right? We answered the first part. There's the critical numbers. So now, let's apply the second derivative test. Applying the second derivative test, f double prime at -1 would be 0. Notice how this first factor, this x plus 1, would become 0 if x was -1. F double prime of -1 is 0. Inconclusive. Similarly, f double prime at 1 is also 0. Again, inconclusive. So we cannot use the second derivative test to determine if there are relative extrema at -1 or 1. We would have to use the first derivative test for those. Now how about -1/7? F double prime at -1/7. -1/7 plus 1, that would be a positive. Negative 1/7 minus 1 is negative, and negative number squared is positive. And then 42x squared plus 12x minus 6. I'm just going to use a calculator here. Let's see, 42 times -1/7. -1/7 squared plus 12 by -1/7 minus 6 is negative. So I have a positive times a positive times a negative. That's negative. And so what that's telling me is, since -1/7 is critical, and the second derivative is negative, that means the original curve is concave down there. So that means I have a relative maximum at x equals -1/7. All right, so now let's complete the exercise. Let's use the first derivative test to classify the critical numbers. So let me get a little bit more room here. All right, so my number line, my critical numbers were at -1, -1/7, and 1. So here's my number line, applying the first derivative test. Here's -1, here's -1/7, and here's +1. And let's see, f prime at, how about -2. Using the factored form, I would have -2 plus 1 is -1 squared, which is positive. -2 minus 1 is -3 cubed is negative. 7 times -2, that's a -14 plus 1 is negative. So then that's a positive. F prime at, how about, what's a number between -1/7 and -1? How about -1/2? -1/2 plus 1 squared, that would be a positive. -1/2 minus 1 cubed, that would be a negative. 7 times -1/2, that would be a -3.5 plus 1 is a negative. Again, positive. A number between -1/7 and 1, how about 0? F prime at 0, that should be easy. 1 squared is positive. -1 cubed is negative. 7x plus 1 would be 1, which is positive, so that would be a negative. And then a number greater than 1, how about 2? F prime at 2 would be a positive times a positive times a positive, which is positive. All right, so now using the first derivative test, what do we see? The function was increasing, stationary for a moment, and then increasing. There's no relative extrema. At x equals -1. Then the function was increasing, then decreasing, changing at -1/7. There is a relative maximum at x equals -1/7, which is the same information we got using the second derivative test earlier. And then the function was decreasing, then increasing, changing at x equals 1. We have a relative minimum at x equals 1. All right, so there's how we could use both of the tests. So we do have to be careful applying the second derivative test. It doesn't work if the second derivative is 0 at that critical number. So if that doesn't work, then you have to rely on the first derivative test. Okay, so that completes our the videos for concavity and the second derivative. And then what's coming up next is we're going to take all of those ideas and we're going to talk more about curve sketching. We're going to see how we can use everything that we've learned so far in mathematics to get some detailed graphs of curves. All right, I hope to see you there.